So it's the habit of all of us language theoretic security nerds to find new and exciting ways to explain this every time that we have the opportunity, just in order to kind of see if another way might produce a different result, since it's such a vast, strange concept. Anyways, this particular way of explaining it, I'm kind of invoking a little bit more about how we develop software and how we search for vulnerabilities, just kind of based on what this is about. So, of course, this is about as much math as fits here. Cantor diagonalization, for the review, is just this theory that you can always construct, given an infinite number of sets, you can always construct another set that isn't a member of that set. So it just tells us that, like, even if you can search an infinite number of things, you're still not going to find all of the things that there are to find. This is just the nature of infinities. The big part of language theoretic security is, of course, about how to banish these infinities. And this is why it's so important. So I'll be using this concept of Cantor diagonalization kind of not as a metaphor, but sort of as a framework for describing why exactly that's so important and discussing a little bit about how we can get there. So bear with me. One quick citation that I wanted to point out is just to Spring's paper, Vulnerabilities Being Dense, an analysis of how many undiscovered vulnerabilities remain in information systems. This was some innovative work that basically describes, and I'm sorry, Jonathan, if you're watching this, I'm going to butcher it. Please just read the paper. We're describing in this basically how sort of with the way that we write software, no matter what we do, we're just going to keep finding vulnerabilities. It's not that they're like dense, like there's always one vulnerability on a line, but given software's sufficient complexity, there always seems to be just a little bit more to find. And I was somewhat inspired by this, and I wanted to develop a framework that helps us understand why that is. You know, when I first entered the information security industry, before anyone was calling it cyber, but actually not that long ago, one of the first things that I was very unpopular because I was always saying, God, it doesn't seem right that every piece of software is always going to have a critical bug in it. You know, it just doesn't make sense to me. It seems that there must be some methodology, whether it's being careful, whether it's doing more or a different type of analysis, writing it in a different framework, writing it in a different language, rewriting it a few times, better testing. Surely one of these things must result in us not having these vulnerabilities anymore, or at least not the same ones, right? This naivety didn't necessarily serve me well, since I proceeded to do commercial software testing and discover a critical vulnerability in nearly everything I came up with, no matter what we said. And it's just kind of, to me, it's why? Why must this be the case? It doesn't seem right, but it is right. So through the study of language theoretic security, why? Well, why is because complexity and security are, as has so famously been said, I think this is gear, opposed. But we love to create complexity in software engineering. Complexity is features. Complexity is our ability to extend the program further. Complexity is often even our ability to test the program. And of course, like maybe if you're a bug hunter, like many of us, it's actually great that we love making complicated systems, because it kind of guarantees that they keep having bugs. But to say complexity is the enemy of security, it still doesn't quite get you to, therefore we should. Well, therefore we should what? We can't stop writing software. I'm sure if we did, we wouldn't have vulnerabilities, but that's not really what we're going for, is it? So, consequent to that, I've been working on this framework. This is very much a work in progress. It's not published yet. It will probably be a paper someday. And the framework that I came up with is basically I don't know yet that it's mutually exclusive or collectively exhaustive, so please take this with a grain of salt. But it's sort of a layer progression in the various the various levels of concept at which software bugs might exist. So the first one is your easy, constraints instantly been violated. You use the functions in band.h, you've got your stir copy here, and I can smash your heap, get a memory corruption exploit, there's some double freeze, something like this. Moving up from there, though, is these issues where maybe two or more parts interact badly, and I have further examples to exploit these. Maybe even above that, where it's not just two or more parts interacting badly, but there's different encapsulated layers that together render the result incorrect. Maybe even above that, there's an external effect that can happen in the environment, maybe something to do with the date and how the computer thinks about the date versus how we think of the date, or maybe it's an external effect, like there's some network traffic from outside that we didn't anticipate. We were using this field, we thought that you specified this field this way, but really some people specify it that way, and my requirements and assumptions are being violated. Above even this are where, my program doesn't even meet the specification. I just implemented the RFC wrong, or, my X509 parser is not right, and then it's not right in a way that wasn't me violating an incident constraint. It's not right in a way that you can give me a document, and that document has a different meaning to you than the document has meaning to me. Moving up from there. What if the specification doesn't mean anything at all? It's completely undecidable. We have to guess what the specification means. You guess one way, I guess another way, on we go. You can see how those are kind of very similar, but they're also very different in how you fix them. Moving up from there, what if the specification doesn't even match your intent? It can be right, it can be perfect, decidable, everyone implements it perfectly, and we still have a security bug because the specification told you to do something that is actually harmful. And then finally, the top layer is that kind of not amenable to computation problem of we did something, we thought it was a good idea, it wasn't a good idea at all actually, and we learned something about society in the progress and nothing about computers. So, example of the first one, a constraint being instantly violated, I think we kind of went over that. One important key for this sort of vulnerabilities is this is the class that you can do things like SAST will find these, fuzzing is extremely good at finding these. Memory corruption vulnerabilities keep remaining a major class, even the plurality of CVs issued. That is another talk, I won't get into that because we only have so much time. But moving on from there, where these two parts interact badly, we've got things like our response splitting attacks. We've got time of check, time of use issues, which interact, the two different parts are interacting in the time domain instead of interacting directly with each other, but there's still that point of interaction. Remember that too, that's a thing. But these vulnerabilities can occasionally be addressed with SAST. These are occasionally addressed with fuzzing, occasionally addressed with some kind of notion of correctness that we recognize. But it's still more complicated than just I use stir copy. The third level moving up, the effects of multiple layers render the result incorrect. This is, what if I have the string false, one layer false, it output encodes false because false is the word that you use to describe 0. But then some other framework interprets, well, that's a string. It's not the string lowercase false or the number 0 or an empty string, so I'm going to evaluate that as true. It's Boolean 1. Thanks, JavaScript. How about where FPU imprecision accumulates error and renders our ultimate output correct? So, we're down there at the IEEE 758 layer, but up here we didn't think about any of that, and now we're accumulating errors that eventually make our result pass some threshold, and oops, the output of the neural net is the inverse of what it was supposed to be. X509 certificates with nulls and identifiers as well, being interpreted differently by multiple programs, can place it in another one of these classes, but it kind of also falls in here. The null termination exists in the C string layer. It does not really exist in the X509 layer, which was designed to accommodate those sorts of things. What happens if there's a null in my domain name? And then, of course, I have to have an example from DARPA SafeDocs, rendering over other parts of the viewport. So in a PDF, for example, what if there's a field that's conditional upon whether the document has been signed 1, 2, or 3 times and displays different contract text and terms to different people. And then the end result is something that nobody signed, but they definitely all signed exactly the document that's there. Bug because the effects of multiple layers, such as the various rendering layers within the PDF, are rendering the final results incorrect or unanticipated. Moving above that, we're sort of out of this is my program or my set of programs into this is my program with the environment. So glitching attacks, analog domain interference, maybe time of check, time of use by a completely different, unrelated set of applications that happen to be using the same storage pool that I am. The proverbial bolt from the blue. These are, of course, as we saw earlier, there was even a talk about this, glitching attacks are much more difficult to bring within your model. You can do this at the physical layer or with redundant computation consensus mechanisms and satellites, but it's still different from my linear code runs linearly and executes in this way every time that it is run. So moving up the conceptual hierarchy with some examples of programs that don't meet the specification, we're getting now into sort of the human issues, missing authorization checks, so-called insecure direct object reference, corrupt documents that cause a denial of service attack instead of graceful failure, the packet of death that took out so many open vSwitches so many years ago. Additionally, the only mention of AI in this that I'm going to make, LLMs spilling secrets. Special case, the specification is structurally impossible to meet. There exists no algorithm to assure that that does not happen. But the program, generally not meeting its specification, not doing what we intended it to do because we designed it in such a way and we wrote and specified it in such a way that it's going to do these things. So each of these meets that. The program is correct. The program just doesn't do the thing that we hoped that it would. Moving again up in the conceptual hierarchy of what if the specification is not decidable. This is where we get those really big hairy bugs like Android master key, where, for example, to refresh everyone's memory, since this is also a very old bug, one signature was checked as to whether it matched the contents of the APK, and the other signature was checked as to whether it was validly signed. So you could, of course, construct something that signed anything at all as long as you had at least one valid signed application ever and knew how to calculate a hash. That's a really hairy bug, but it was the result of an undecidable specification where it was possible to put files with redundant names in a zip, if I remember, or keys that were redundant in a JSON. There were multiple iterations of this bug, and they all mashed together in my mind, but it's something of this form, that ambiguity, which the specification doesn't prohibit. To the extent that there's even a specification for JSON, it is definitely not the case that most JSON parsers reject duplicate keys. It is definitely not the case that most archive decompressors reject duplicate file names, but their behavior differs greatly, and it gives rise to these bugs. And that's because the specification is not decidable. Given such a document, I cannot say whether it does or does not match the specification. Similarly, Office document bugs where the hash maps are incorrect. The specification has this sort of, but not entirely. Example of the 7th category up, 7 of 8, we're almost done this part, where the specification doesn't match our intent. This now is the bane of cloud. We write so much cloud code in memory-safe languages. It's all a giant pile of Java, Python, Go, relatively little C and C++. There's some Rust now being used, and lots of memory safety. Not a lot of that first class of bugs where you instantly used the machine wrong and violated the way that you're supposed to use the platform, but the specification doesn't match intent anyway, because your authorization policies don't match the rules that were written down in your organization for who's supposed to be allowed to do what. And that one arguably was a big part of the Capital One hack that happened a few years ago. Misapplication of anomaly detection as well. Perhaps we specified that something was an anomaly. It turns out that it's something that happens with some frequency in a particular use case, but when it happens, we reject it because our model didn't include it. And now we've prevented our operators from fixing prod, or we've prevented somebody from making a stock trade that's in response to a so-called, shall we say, black swan event. Similarly, arbitrary hard limits. I can say, great, nobody should be allowed to log in as this particular user more than 3 times in an hour if it fails. Well, now I can just permanently prevent that user from logging in. Good job. Arbitrary hard limits that cause denial of service. So I intended to prevent brute force attacks, but what I actually specified was that anyone can deny service. And then finally, example 8, the ones that are not amenable to any kind of computational analysis so far as I'm aware. The specifiers were not aware of what their requirements actually were. These examples, I also like the example of an SMTP open relay. When that was a thing, we didn't actually know about unsolicited commercial email yet. And then we discovered unsolicited commercial email in very, very short order. And we had to amend what our requirements were. We require that there be some concept of being authorized to send email, and we never fully recovered from that bug. Lack of the content security policy in HTTP. And long ago we didn't realize that allowing your web page to be embedded in an iframe was actually potentially a problem. No fallback detection in old TLS. This wasn't really conceived of. It turned out to be completely necessary due to SSL strip attacks, but long ago. Most timing-derived info leaks existed long before we really understood that people would time network requests to determine what some aspect of the underlying computation being done, or whether there were results to filter through, whether you said there were or not. Similarly, zip bombs, just nobody thought that it was necessary to prevent this. It's not within the specification that you can't make zip bombs. Certainly you can use RLE to encode an essentially unbounded amount of data. But this was a plague of network administrators for years. And then, importantly, Rowhammer. No one had considered the possibility that there might exist some physical layer attack that you could exploit from software to flip bits in memory and completely violate the computational model. The specifiers were not aware of that requirement until it happened, and then we finally started fixing it. So that's sort of, again, what this conceptual hierarchy is for. It's to allow us to say, here's layers. We can address these problems with these tools. We can address these problems with these tools. And then maybe there's some other types of thinking that we need to do to address the problems at the higher layers. So again, take the framework with a grain of salt. I need to do a lot more work on this, but it helps me understand why there's so many software bugs and why the software bugs keep coming up in different ways, and why one software bug might be really big and difficult to fix and important and innovative, where another one might be, yet another zero-click exploit in that stupid phone operating system. Can you go elsewhere with that, please? Why are some bugs more common than others, and why are some bugs bolts from the blue that are innovative and creative and nobody would have thought to check for them before? But also, which parts of vulnerability discovery and remediation are we likely to be able to automate, and which are we not? And it almost brings me to this place where I feel like we're a number of different fields all agglomerated into one. We're correctness, but we're also, at the upper layer, at the 8th level, the anthropology of computing. Is spam bad is simply not a technical question. It's a question about email's role in our society and how we communicate with each other, and the ethics of engineering. It's a question about stakeholders and enumerating which stakeholders exist, whereas the lowest level, by contrast, is not about stakeholders at all. It's literally just about program correctness. So a brief detour a little bit into what these multiple fields all do together. Well, it's always been a kind of a pet peeve of mine that we test software this way. You write your unit tests, you try and come up with as many representative cases as possibly you can come up with. You test, does my thing work if I set a length of -1? Does it work if I set a length of 0? Does it work if I set a length of 5, 6, 7? And if you wrote a proof by induction of this in a proofs class, you would fail. There's no way. I did that once and they marked it wrong. You can't test software this way either. We'll get why, but I have a hunch that we already have some idea. So this proof, not so good, but this proof is the state of the art for basically all unit and most integration testing. So software testing attempts to address everything short of incorrect specifications, but you can't actually test every case. So I'm kind of laying out a largely unsolvable problem here. How do you write good unit tests if these unit tests don't work? But at the same time, it is obvious that you cannot, for the vast majority of programs, not for all, maybe you have an enum with 6 members and it has no interactions with anything else, then you can do this. You generally can't perform exhaustive testing of your software, and you generally don't want to. So how do we measure security testing? I don't know. This to-do will never be fixed. We have a lot of theories about how we measure security testing. Everything from one thing that I used to do just kind of as a stopgap. When we test this, did we find anything at all? Did we find any vulnerabilities? Was the text of our testing even responsive? This, by the way, one of those favorite questions, not amenable to computational solution, whether the things that I said about your program were interesting and demonstrated that I looked for vulnerabilities. Where would I look for vulnerabilities? If you knew, maybe they wouldn't be vulnerabilities at all. So measuring these unknown unknowns is kind of torturous. You can't do it with unit testing. You can't do it by having some percentage complete metric because it's an unknown unknown. You don't know what you don't know until you know it, and then it's no longer an unknown unknown. So you've always found 100% of the bugs that you know about and 0% of the ones that you don't know how many of them there are. There's literally no decision procedure for this. And the fact that measuring security testing is not really currently meaningfully possible is a significant contributor to why computer engineering is among the only fields of engineering that ships things that kind of we know that they're probably broken and we don't know how and we don't know what the impact will be and we don't know when it will happen and we don't know what to do if it does, but we ship it anyway. You don't let people on a bridge like this. But you definitely let people use software that gates major decisions in their lives on this. So of course, my limited understanding of ICS, I understand that we tend to say, okay, well, the computer is just going to do what the computer is going to do. Someone described to me just the other day a water system. And well, this computer with its PLC, somebody might be able to hack into it. The security on this is not the greatest. It has some RCE in it. It has some maybe default passwords, God forbid. And they can get in and they can shut my water valve off, turn my water valve on, shut my water valve off, turn my water valve on. The name for this contention is, I believe, water hammer. And to break the water system. So what did they do? Well, they didn't fix the PLC, because they don't know how, and they don't know that they can, and it's not amenable to computation, and its complexity is unbounded. They put a damp on the relay that said don't flip more often than X in the relay rather than on the PLC. That's the best that we can do. We can't fix it in software. Why? Well, so the density of vulnerabilities is coming at us from these three things. Software testing and vulnerabilities, pretty much non-correlates. The best tested software has vulnerabilities. The worst tested software has vulnerabilities. Lines of code coverage and test usefulness. I can't count how many people I've seen measure this and say, well, our goal is to get up to 100% lines of code coverage. They're non-correlates. And test completeness against external predicates, mostly unknowable unless you design your software in very specific ways. There's a little bit more, though, about how that line of code coverage and test usefulness are not correlates. It has within it the clue for what to do about this. Line of code coverage does not correlate to complexity, does not correlate to the number of interactions, does not correlate to the number of use cases. There's some very complicated code fit on one line and some very trivial code spread across thousands. And you can have code, if you're writing in a language like Java, that maybe there's a lot of that code that just the compiler thinks it needs to be there, but it doesn't need to be there. You can never reach it. That's gotten better over time. This Java exception handling is a big one with that. You declare that this exception might be thrown. You can verify that the condition where the exception is thrown never occurs. Can't reach inside the package to get rid of it, so you've got to handle it. Now your handler is untested code, syncs your code coverage metrics. This is not the way. The way is to test the complexity, to test the number of different things that can happen, the number of different situations that your software can be put in. And when we're all finding these innovative vulnerabilities and coming and presenting them here at WOOT, a lot of the time that's what we're doing. We're saying there exists a subsystem here. That subsystem has some enumerated number of cases. We're going to go through those cases and look for interesting things about them and figure out whether any of them match something that is in our threat model. At least when I try to find bugs, I try to do that. I don't know how other people find bugs, and it's very good that there's a great diversity in how to find bugs. But all of these measures, they're not quite what we need. But the reason that I didn't just splash up here, all right, that's it, we're done, that's how you do it, is because the way that we write software, we generally can't enumerate those either. So what is the density of vulnerabilities in Turing-complete code? Any non-trivial property of a Turing machine is undecidable. That's Rice's theorem. We generally accept it as true. It implies that the number of test cases that we would need to go through to find all of the vulnerabilities in such software approaches infinity. That's why we can't find them all. That's why we keep finding them over and over and over again, because we're on a random walk through an infinite space. So back to language theoretic security, and no more doomsaying for a moment. You old automata. There are certain levels of complexity, as we love to point out, where it is possible. If not easy, it's possible to answer some of these bounding questions, right? In a Turing complete system, Rice's theorem reigns supreme, and you can't find them all. In a pushdown automaton, you can't necessarily enumerate them all anyway. When we say we have a recursively enumerable language, what we mean is that the number of things in the language is countably infinite, rather than that you can actually sit down and enumerate them. But in general, if the thing's only got one stack, it's usually possible to make some proof by induction of what is actually going on there. I'm playing fast and loose with this. Please don't ask me for a proof later. Or any simpler language than or at deterministic context-free grammars, you can demonstrate at all this thing called the general equivalence problem, which is to say if your specification is machine readable and transducible in some way to this, maybe at least you can show whether your program meets the specification. Remember that hierarchy, concordance with the specification is not the zenith of security by far, but it at least gets you through. And when we start to put those bugs into those classes, right? And for actual proofs of this stuff, please check out langsec.org. But when we start to put vulnerabilities into those classes of conceptual frameworks, we can say, okay, if we do this thing that gets us coverage on all of the levels of the conceptual framework below this point, we know at least that we can deal with those vulnerabilities. Your fuzzer's probably not going to find very much. You're going to have to start thinking about how the machine is used in the social context in which it's used before you're going to start finding vulnerabilities in it, I think. I haven't verified that. That's the paper. Diagonalizable cases that are simply not amenable to induction, however, why I put Cantor's theorem, Cantor's diagonalization theorem up above there, is how do you test that, right? If it's diagonalizable and it's an infinite space, you can sort of imagine, an n-dimensional solid, and the dimensions of each of that solid are individual modes of interaction or individual interaction points with the system from each stakeholder. You imagine that there's areas within here that are vulnerable, and there's areas within here that are intended, and there's areas within here that are benign. But if it's an infinite n-dimensional space, good luck to you. That's not just diagonalization. 2 dimensions was enough for Cantor. How do you test it? Of course, the open challenge as well is correctness of the specification, even if you can test it, and whether the specification is machine readable, which is also ridiculously important to being able to put any of this in practice. So, some strategies. Developers should write static analysis rules rather than simply writing unit tests. I would love that. I'd love to see that. But which ones? And which tests right now do we write? Test selection right now, in my experience, has a proclivity to be done in one of 2 ways. Either it is testing that is done because some terrible mess was made, and we need to make sure that that never happens again. And also, they're kind of a developer's random conceptual walk to make their manager happy and make the code review process happy that they wrote some tests. I'm not aware of any methodology that really lets you say, these tests are good and those tests are bad. It's so situational based on the way that we write software. So, I can generally say, well, it seems like I know what a bad test is when I see it. You tested only one use case, and the use case is, trivially reducible to 1 = 1 or 0 = 1. But, a good test, it's a little bit more subtle. How about tests that test things from the external environment? How about static analysis rules that test things from the external environment? But if we write static analysis rules, at least we can stay out of those lower levels of the conceptual framework, where we tested 1, 5, and 7, but we didn't know for some reason that prime numbers over 1 million are a special case. So that's the proof by induction coming back. Some other strategies. Memory correctness, it turns out. You can write it in Rust, you can write it in C. I really liked the trolling that I got earlier, language theoretic security being about what programming language you write in. It's super not. I don't mind if somebody writes a new program in C, as long as they do this. Memory correctness in such a language is, modulo certain cases like DMA, ternary conditional. Either I know that it's memory correct and I can show it with static analysis rules, I know that it's not memory correct because there's obviously an unbounded memory access, or I can't tell. Now, if you reject those latter two cases, then you have a memory-safe program. And this requires a little bit of work on the behalf of developers to discipline themselves away from writing these things where, well, I think it's right, but I can't show it's right. You have to do a little bit more work. But in general, any program that you would want to implement can be implemented on one side of this ternary conditional without straying into the other two. So either of those two answers mean don't merge your code, because clearly there's a static analysis rule check in your pipeline for commits in your repository, right? Your SDLC does this, yes? Two solutions, one open problem. Say we do these lightweight formal methods and we do static analysis. How about the compositional properties of models? How about if we do have DMA? What if our device driver code plus DMA plus a device results in a wild read or write that maybe our test cases for the driver might not themselves check for? What's happening on the PCI bus versus what's happening in the driver code? Very, very, very few properties are actually closed under composition for complex systems. Thinking back to the standard finite state automata theory, you know that regular expressions, certainly if you compose them together, they're still regular. But you don't know that for other types of automata. If you have a push-down automaton and now you compose them together and it has two stacks, oh no, compositional property violated. So a person must be careful, but you can do integration testing with these sorts of systems, but beware, because you might end up in a scenario where even though you're doing integration testing in each system in isolation, looks like it's correct and looks like it's simple enough to analyze. It's not necessarily the case that the composition of these systems together is amenable to the same type of analysis. This is something that we learned from the decline of the irrational exuberance of object-oriented programming in the 90s. If you'll recall, it was thought that by composing well-encapsulated objects together in specific ways with contracts and interfaces, that clearly, if they were correct in the individual and their compositions were done appropriately according to spec, they would obviously be correct in the large. This turns out to be about as far from the case as you could possibly get. So back to what I was saying before about the vulnerability topologies. They're kind of existing as these n-dimensional solids, and we're walking through random space, and here's the vulnerable region. Maybe an entire plane of this is vulnerable because there's one of those level 1 conceptual framework issues where we just use the framework wrong, and if one stakeholder inputs this one payload, then no matter what any of the other stakeholders are doing, it's definitely RCE. Sometimes they're a little bit smaller and a little bit harder to find. If I execute the following code whilst glitching the microcontroller with power, it might, sometimes but not other times, depending on how many times I've attempted it so far in some internal capacitor charge, might allow me to bypass bootloader signing. So each dimension is representing something, and the smaller that area, the harder it is to describe the vulnerability, the harder it is to find it. And that forms our long tail as we do our random walk through this. And I suspect that there's a statistical model here. If someone were to sit down and formalize that, it could be fun. But what I really would rather do is figure out some way to limit the size of that n-dimensional space. And that's, again, where our making careful specifications comes through. If I can show that some classes of the use cases are equivalent, especially the ones that are recursively enumerable but not finite, and I can show that there are only so many such classes, suddenly, along that dimension, there's a wall that you'll eventually walk into if you keep walking the random space. Eventually, it won't be necessary to fuzz the program for RCE payloads until the end of time, at least along that one axis of interaction. Similarly, vulnerabilities in complex systems. So based on the aforementioned, they could absolutely be finite. Test cases that we need to have are uncountably infinite. And there could be even multiple vulnerabilities per line. So we don't have a lot of metrics for this when our programs are complex. It's hard to say whether you've tested the program adequately. It's hard to say what your test coverage means. It's hard to say how many vulnerabilities there are. Looking back to Spring's paper, it's not about lines of code. And there could be one or less vulnerabilities per line of code as well. And those vulnerabilities might not currently be meaningful. Maybe the external environment changes around the software and makes the software wrong where previously the software was right. So limiting the space is accomplished via constrained interfaces. This is the spine of what we call LangSec. If you remember the paper earlier discussing PHP's extract and how it allowed you to just overwrite parts of the environment just like you had an arbitrary read-write primitive in a piece of native code. That's the opposite of this constrained interaction, right? We have this concept in language theoretic security, I'll touch on this later as well, called the shotgun parser, where you allow your input to cascade its effects through, like a shotgun blast, through your program's state. And it's impossible to pick it all back up again and remove it once you figure out that you ought to have rejected some piece of input. Because you're parsing a little bit, and you're taking a conditional on it, and you're parsing a little bit more, and you're writing stuff into memory, and you're losing track of it, and you're putting another conditional in. That's what we're doing with primitives like that, and that's why that's still somehow, decades later, a source of bugs. This is why LangSec people are always on and on and on about shotgun parsers and the recognizer pattern, because if you constrain this, right? If you fail to constrain this and you have PHP extract, that's one of those, like, maybe the state that can be put into your program by the external entity is uncountably wide. They could put as many of those little things as the payload will allow them to put, the payload size limit will allow them to put. But if you put the recognizer in front and you say, well, this request has some odd parameters, why is it specifying that? And you reject it, because that's not a field that I was expecting, suddenly it's very narrow. All of that extra complexity just goes away. You don't need to test it. You know that all of those words are equivalent. They're all equivalent to halt. So back to programming languages. I like to think of them like poetry. You know, how do you read the code? When I read your program, what does it tell me? Does it tell me anything? Does it tell me too many things at once and I'm overwhelmed? Does it tell me things in an order that is natural, that expresses your intent? Or does it tell me things in an order that's like, you know, your poem that you wrote in second grade and you're just rhyming things and it's more important that you rhyme them than that they really even make any sense? Which is a lot of how we write heavily patterned code, by the way. And then is it precise, or is this intent open to interpretation? Is this self-documenting code, or is this not self-documenting code? And again, you know, this is language theoretic security. I don't care what language you write it in. We'll get to another kind of language, though, in a moment. But lightweight formal methods can be applied to this as much as they can be applied. You know, you can apply them to C, you can do them in Rust. The most important thing is doing the analysis at all. You have to actually read it. And that's why it's so important to write code in this way. As the number one question that I was always asking as a security analyst was, how on earth does your concrete implementation work? I see your abstractions. I'm very proud that you have managed to encapsulate this program, but you know, the implementation is in another castle. Please also give me that, because what I need to know is whether or not you've used the banned functions and have wild read-write primitives in memory, and I need to know whether you're using MD5 to check whether something is authenticated, and I need to know whether you implemented the business rules in this or not. And the fact that the function's name says this and it's in some other module and it passed tests, it doesn't mean anything to me, but the typical response that I would get from this is reject the premise of the question. You know, what do you mean? What do you mean the implementation? Someone else wrote that. That's not in scope. And that doesn't work. You have to actually read the code. We work in the concrete as security practitioners. We care whether the shell actually gets popped. It's always concrete. And bugs like to hide between abstractions too, and the more of those abstractions, for example, a very popular one, ironically enough for testing, you often end up with a dependency injection framework. Well, there's this undefined interface. I know about the test implementation, and I know about the implementation that you intended. Are there any other implementations? Oh no, random walk through the universe to see whether or not there are. You can't show the absence. So there's a phrase, quand c'est flou, c'est qu'il y a un loup. If it's not very clear, well, that's where the problems are hiding. Don't obfuscate the code with unnecessary abstractions, or if you do, at least leave some way to analyze, you know? Because if the implementation of something is purely runtime injected, it's necessary to analyze that thing as effectively an external system. But it's so often the case that when we build these layers of abstraction, we kind of assume that the thing is trusted because we wrote it. And then we've got that shotgun parser. My external module that I don't know what it does might as well be a read-write primitive. In some cases, it's the module that implements a function that allows an attacker to execute arbitrary code. It implements a system keyword in a language, a domain-specific language where there was no system keyword before. And if you don't know that that can't be there, it might be there, and you'll never find it out because of unnecessary complexity. Another one of the ways that we kind of violate this conceptual framework is abstractions. I actually like abstractions. I'm not sitting here saying write all of your code imperative and don't ever abstract anything and stop using high-level languages. In fact, quite the opposite. But it's important to remember that just as we don't really have a good way of making sure that tests are complete, or we don't have a very good way of analyzing the computational or the compositional properties of certain types of code, abstract filters also don't exist. And any attempt which is trying to say, these phrases are bad and these phrases are good, these abstract filters just don't exist. Take, for example, a web application firewall. There's one of these bolt-on products that we say, well, here's all the enumerated classes of exploits that we know at the lowest conceptual framework up to where we can get. We know that SQL injection is one of them. We know that cross-site scripting is one of them. They've got their CWEs assigned. We're going to find them all. And the way that we're going to find them is we know exactly how to characterize them, and we know that we can put a definition for them in our web application firewall, and that definition is decidable, and I can make sure that it's complete according to all of the payloads that we've ever seen used. Well, okay. I've got my little API. My API is managing some SQL servers. That's what I do all day. And sometimes I want to send some SQL to them to run because I need to change the schema. Oh no, SQL injection, can't have that, out it goes. So it very quickly breaks down because there aren't bad words. Apostrophe is not a bad word. We so often treat it like one, but it's really just not. Neither is backtick, normal printable characters. Similarly, to say, select star from is not a cuss word that users should never say. Users very often need to say that. We often need to say that. What if you tried to submit a paper and the web application firewall said SQL injection? So that's not a tenable approach. It just doesn't work. The semantics of everything come from how it's used. The context matters. If the payload is in an academic paper and you're studying it, that's very different from if the payload is incident to your program. But this is why attempts to filter don't really work as well as attempts to try to make the program resilient to whatever input might come its way. That is to say, the program can reject the input, but you are unlikely to be able to construct something that can protect programs, the semantics of which you are unable to understand. And that's where we come back to limiting complexity. So remember, preventing shells in SQL injection and XSS, it's only one goal among many. Really, there are a plethora of requirements. We might be worried also about whether somebody is allowed to specify an amount of greater or lesser magnitude in many applications, like transferring money or changing the flow rate of valves. We've got those safeguards in place for a reason. It's odd to say that numbers over 1 million are bad in a generic context, just as it's odd to say that select star from is bad regardless of the context. The reason that I talked about all of that, even though I know you already well know it, is to introduce that every program is fundamentally a limited purpose VM that has as its machine code language that program's input. So my document that I put into the thing, my regular expression that I put into the regular expression parser, they're the same in my mind. It's a little program. My program that operates it is a limited purpose VM. And if I want to analyze that limited purpose VM, the more limited that purpose is and the more finely bound the complexity of its acceptable meaningful input languages is, the easier of a time I'm going to have analyzing that. And so when we go back to saying complexity is the enemy of security, this is what that means. Make that VM as simple as possible. Make that machine code language as simple as possible. Don't make it any more complex than you need to be. You'll just do a bunch of extra work doing the security analysis and fill your world with all of these unknown unknowns. So input safety being defined by semantics implies that programs are VMs that run their input. So thinking a little bit about the tools that we need to actually apply these concepts. SAST, a constraint has been instantly violated. I used the computer wrong. This is one of those things where I can find the cases with the SAST where my input language that my VM is running does have bad words in it, and I can prohibit anyone from saying those bad words, or I can make those bad words no longer meaningful, and then I can deal with, I'm going to hazard, more work needs to be done here to actually crystallize this, which is why this isn't a paper yet, but most of the CVEs have often lived here. And I think that we really need to get off this particular hamster wheel by doing the proofs by induction. Even doing just the barest little minimum part of this would probably free up a lot of our time for higher and better pursuits. Now, we recognize, of course, the existence of legacy code, and we recognize the sheer impossibility of rewriting all of the legacy code according to modern precepts. But if we're willing to do things like rewrite large fractions of Linux kernel in Rust, why not do this too? Why not change out a bunch of unit tests for static analysis rules? When we want to move up to the next domain, we can see sort of if you can write a constraint, it's better to write the constraint than to write a test case. If you have to write a test case, see if you can exhaust the relevant cases and know that some bugs will likely remain unless you can prove the compositional semantics of what you're doing by induction or by exhaustion, one or the other. This gets us up to a point in this conceptual hierarchy. Item 4, those external effects on one layer that can violate a requirement, it kind of sucks there because the universe is not a deterministic finite automaton. I hope I have free will. I don't know. I mean, but it's not very useful to reduce in much the same way that we can reduce what's happening inside a computer to a finite state automaton with an amount of state that is known, as long as we don't add more RAM anyway or start storing things in the external network interface in the cloud or whatever. But when an external effect enters into this, our ability to fully analyze those use cases and bound their complexity kind of breaks down. So it's on our side of it where we're making the program that we really need to be narrowing in what kinds of things we might be willing to accept, because modeling the external environment is so difficult. So moving up from there, sort of toward the end of this, and then I think I'll open it up for questions since we've got a little bit of time left. It would be nice to stop having to play at the lower layers, and maybe we could devote more of our resources to this. What is the specification? Does the program actually need it? Is the program doing the kinds of things that we actually want the program to do? Or is it sort of a Conway's Law product of its organization and nobody really knows what it does? That's a very interesting problem that we could solve if we didn't have to constantly find your XSS and SQLi and stack smash RC. The future of security work really should not be finding more gotcha vulnerabilities because there's an infinite number of them. It should be figuring out why those vulnerabilities keep cropping up, dealing with the aspect of computer engineering that allows them to keep coming up, and then ideally moving on toward our specifications, our stakeholders, figuring out how to engineer programs progressively and figuring out what, if anything, our programs are doing in society, and is that the kind of thing that we want. The diagonalization will always be an issue because these things, these 4 things up here, the specification not being met by humans writing code, the specification not being decidable at all, the specification not even matching the intent, and the specifiers not even knowing what they wanted to do, those things will always share an infinite space in that I wish I had a diagram of it, sort of this n-dimensional solid, which I can't draw a diagram of definitionally, of what can happen in your program. So put as many of those things as narrow as possible. And I hazard that probably we will be able to move on and stop finding the same lol vulns over and over and over and over again. So that's about all I've got, but I'm quite happy to open for questions.